Hello and welcome. Tonight we will journey gently into the world of quantum computing. In this calm and quiet exploration, there's nothing you need to do at all. Just lie back, relax, and let the soft words wash over you. We'll start at the very beginning, tracing the story of how quantum computing came to be and slowly unravel what it is and how it works. Everything will be explained in a simple, soothing way, so you can drift in and out of listening and still absorb the ideas. If your eyes grow heavy and your mind starts to wander, that's perfectly okay. This time is for you to unwind as we speak softly about the fascinating yet gentle realm of quantum computing. Let's begin our journey through time and knowledge, step by step, in a calm and peaceful manner. Our story starts long ago at the turn of the 20th century, when science first began to discover the mysterious behaviors of the tiny particles that make up our universe. Over 100 years ago, the groundwork for quantum computing was quietly being laid without anyone knowing it at the time. In the early 1900s, physicists like Max Planck and Albert Einstein discovered that at the tiniest scales, energy and matter behave in surprising ways. They found that energy comes in little packets called quanta, and that particles can act like waves. These discoveries were the birth of quantum mechanics, a new kind of physics that revealed a world full of uncertainty and possibility. It was a strange and fascinating realm where an electron could be in many places at once, and where simply observing something could change it. Scientists of the day were amazed and sometimes puzzled by this quantum world. Even Einstein, as brilliant as he was, felt uneasy about some of these ideas. He famously called one quantum phenomenon spooky action at a distance because it was so mysterious. That phenomenon was what we now call entanglement, a deep connection linking particles even across distances. In the 1960s, physicist John Bell devised a famous theorem as a test, asking, could there be some hidden ordinary explanation, or was quantum theory's entanglement real and unique? Experiments in the 1970s and 1980s, notably by Alain Aspect and others, conclusively showed that entanglement is indeed real and cannot be explained by any classical tricks. The spooky action Einstein worried about was proven to be a genuine aspect of nature. This validation of quantum mechanics gave scientists confidence that these strange effects were not just theoretical quirks, but could someday be used in practical ways. While these early physicists were exploring the quantum world, the age of computing had not yet begun. But by the mid-20th century, classical computers started to appear. Big machines filled with vacuum tubes, and later with tiny switches called transistors. These classical computers run on bits, pieces of information that can be either 0 or 1, like tiny light switches that are off or on. As decades passed, classical computers became faster and smaller, following what we call Moore's law, which is the observation that computing power tends to double every couple of years. By the 1960s and 70s, computers were transforming how we live and work, but they were still completely based on the classical physics of everyday life. They didn't yet touch the strange quantum physics that scientists had uncovered. However, even as classical computing grew, a few thinkers began wondering, what if we could use those strange quantum properties for computing? One early hint of this came around 1969, when a physicist proposed a concept of quantum money, a form of banknote that could be verified by the laws of quantum mechanics, making it impossible to counterfeit. It was a very imaginative idea, and it showed that quantum principles might someday be used in new technologies. Still, at that time, quantum computing as a field didn't exist. It was just a glimmer of an idea waiting for the right moment. That moment began to arrive in the early 1980s. In 1981, a renowned physicist named Richard Feynman gave a talk that is often considered the spark that ignited quantum computing. Feynman pointed out that simulating nature, things like molecules or particles, was incredibly hard for classical computers because nature itself is quantum. He suggested, in his gentle and insightful way, that to simulate quantum physics properly, you might need a computer that itself worked on quantum principles. In other words, he imagined a machine that obeys the same strange rules as the particles it tries to calculate. This was a profound idea, a quantum computer. Around the same time, other researchers also started laying theoretical foundations. In 1980, a physicist named Paul Benioff had proposed a theoretical model of a computer that ran on quantum mechanics, and a few years later, in 1985, another scientist named David Deutsch published a description of a universal quantum computer, a blueprint, in theory, for a computer that could harness quantum mechanics for any calculation. These were quiet early steps, theoretical ideas more than physical machines, but they marked the dawn of a new quest. The world now had the concept of quantum computing, even if no one had built a real quantum computer yet. It was an exciting notion among a small group of scientists, yet still very much a dream. Around that time, in 1984, two scientists named Charles Bennett and Gilles Brassard took another step in the realm of quantum information. They developed a practical scheme for quantum cryptography, using quantum particles to share secret keys securely. This showed that quantum principles could be applied not only to computing but also to communications, laying the foundation for what we now call quantum key distribution. As the 1990s came, that dream started to feel a bit more real. In 1994, a major breakthrough happened, not with hardware, but with an idea for a calculation. A mathematician named Peter Shor discovered an algorithm, basically a recipe for a computer program that could do something astonishing on a quantum computer. Shor's algorithm could find the prime factors of a large number dramatically faster than any classical algorithm known. Why was that so important? Because factoring big numbers underlies much of the encryption that keeps our digital world secure. With a quantum computer running Shor's algorithm, one could, at least in principle, break the codes that classical computers cannot crack. This discovery was a wake-up call. It showed that if we could build a working quantum computer, it wouldn't just be a scientific curiosity. It could solve certain problems that are practically impossible for classical computers. People often say this was the moment the world took quantum computing seriously. Another quantum algorithm emerged around the same time, in 1996, discovered by Love Grover. Grover's algorithm showed that a quantum computer could search through unsorted data much faster than a classical computer, potentially finding a specific item in a huge database with far fewer steps. These algorithms, Shor's and Grover's, were like beacons illuminating what might be possible with quantum computation. They were still just mathematical ideas written on paper at that point, because no quantum computer existed yet that could run them for any meaningful problem. But they gave researchers something concrete to strive for. Also in the mid-1990s, scientists began tackling one of the biggest challenges in this field, the fact that quantum states are very delicate. They knew that qubits, the quantum bits, would be prone to errors because the slightest disturbance could nudge a quantum bit and mess up a calculation. In response, clever minds like Peter Shor, the same Shor of the factoring algorithm, devised methods of quantum error correction. It was a way to use multiple physical qubits to represent one logical qubit in a robust way, so that even if some of them got disturbed, the overall information could still be preserved. This was an important theoretical step, like designing gentle safeguards for a very fragile process. By the late 1990s, technology was catching up to theory, at least in baby steps. In 1998, for the first time, researchers managed to run a simple quantum algorithm on actual quantum hardware. They used a tiny 2-qubit quantum computer built using the nuclei of atoms in molecules, controlled by magnetic pulses, a technique called NMR, nuclear magnetic resonance quantum computing. With just 2 quantum bits, they solved a very basic problem, known as Deutsch's problem, another small algorithm to show that quantum computation worked in principle. It was a small demonstration, but imagine how exciting it must have been. For the first time, a calculation was done by harnessing those ghostly quantum superpositions and entanglement in a real device. Shortly after, a 3-qubit quantum computer was also demonstrated. These devices were not anything like a practical computer. They were more a proof of concept, running in physics labs with careful tuning, but they proved that the dream could be real. Moving into the early 2000s, progress continued steadily. In 2001, a team of scientists used a 7-qubit quantum computer, again using nuclear magnetic resonance techniques to run a simple version of Shor's algorithm. They managed to factor the number 15 into 3 and 5, which might seem trivial, but it was a landmark. It showed that Shor's algorithm could actually work on real quantum hardware, however small. Each year, researchers around the world were learning to control qubits a little better, to keep them stable a little longer, and to string more of them together. They experimented with different physical forms for qubits. Some used trapped ions, individual charged atoms held in electromagnetic traps, which can be manipulated with lasers. Others used superconducting circuits, tiny loops of superconducting material that carry current in quantum states, which have to be kept extremely cold near absolute zero. Others still tried using photons, particles of light, as qubits that could travel through optical fibers. It was as if there were many paths up the mountain, and nobody yet knew which path would reach the top first, so explorers were trying them all. During the 2000s, these efforts remained mostly in laboratories. Quantum computers were still very small, a handful of qubits, and could only maintain their quantum states for fractions of a second. But bit by bit, the field moved forward. A notable milestone in this period was the founding of a company dedicated to quantum computing, D-Wave Systems, in 1999. This company, based in Canada, took a different approach known as quantum annealing. Instead of gate operations like the ones needed for Shor's or Grover's algorithms, their machine was designed to solve optimization problems by gently coaxing qubits to find the lowest energy solution to a problem. In the early 2000s, D-Wave and others worked on this approach, and by 2011, D-Wave announced the first commercial quantum annealer, a system that they claimed had 128 qubits. This machine was not a general-purpose quantum computer. It was specialized, and there was debate in the research community about how quantum it was in practice. But it was a sign that quantum computing was transitioning from purely academic research to something that companies were investing in. Around the same time, academics and industrial researchers focusing on the more general gate-based quantum computers were making significant strides too. In 2016, a big moment arrived when IBM put a small quantum computer online for anyone to experiment with. IBM made a 5-qubit quantum computer available through the cloud as part of the IBM Quantum Experience. This was revolutionary in its own quiet way. It meant that you didn't have to be in a specialized lab to try out quantum computing. Researchers, students, and enthusiasts worldwide could run small experiments on an actual quantum processor from their own computer. It signaled that quantum computing was maturing, not yet ready to do heavy lifting, but ready to be explored by curious minds everywhere. In the late 2010s, the field accelerated even more. Tech giants like Google and IBM, as well as startups and university labs around the globe, were all racing to build devices with more qubits and less error. Qubit counts grew from single digits to tens, and the coherence times, how long a qubit can stay in that delicate quantum state, were slowly improving with better designs and error mitigation techniques. Researchers developed more sophisticated ways to entangle qubits and control quantum gates with high precision. It was still extremely challenging, like trying to choreograph a dance with dozens of ghosts, but the progress was undeniable. Then, in 2019, there came an announcement that made headlines beyond the scientific world. Google reported that it had achieved quantum supremacy. Quantum supremacy is a term meaning that a quantum computer performed a task that no classical computer could feasibly do in a reasonable amount of time. Google's quantum processor, named Sycamore with 53 qubits, had performed a specially designed computation, basically checking the output of a random quantum circuit in a matter of minutes. They estimated that the fastest supercomputers would have taken thousands of years to do the same task. To be fair, this task was a bit esoteric and not something with direct practical use, and some other researchers, including a team at IBM, argued that classical computers could be optimized to do it faster than Google initially claimed. But regardless, this was a watershed moment. It was the first strong demonstration that a quantum machine, even a very specific one, could outperform the world's best classical machines on at least one task. It was as if the quantum computer had won a small race that no classical computer could even finish. For many, it felt like proof that this technology, still so nascent, really does have unique power. After 2019, investment and interest in quantum computing skyrocketed even further. By the early 2020s, governments were launching national quantum initiatives, and companies were unveiling roadmaps for even larger quantum processors. In 2021, IBM unveiled a quantum chip with 127 qubits, and in 2022 they announced one with 433 qubits, showing how rapidly the hardware was evolving. The quest was no longer just to add more qubits, but to also make them better qubits, more stable, less error-prone. The term NESQ, which stands for Noisy Intermediate Scale Quantum, became a way to describe the devices of the current era. They have a moderate number of qubits, tens to a few hundred, but they are noisy, meaning errors are still frequent and they can't run very long computations before the noise overwhelms the result. Researchers today are deeply focused on improving error correction and finding ways to scale from these NISQ devices to the truly powerful quantum computers of the future. As of now, in the mid-2020s, quantum computing stands at a delicate and exciting place. It is reminiscent of the early days of classical computers. If you think of classical computers in the 1940s or 1950s, they were large, experimental machines that often malfunctioned. They were not yet the robust everyday tools we have now. Quantum computers today are similar in that way. They are finicky and need special care. Most need to operate in extreme conditions like ultra-cold temperatures a fraction of a degree above absolute zero, or in high vacuum chambers to protect the qubits from the environment. They are managed by teams of specialists who coax them to run algorithms that are carefully chosen to fit their limitations. They aren't performing broad miracles yet, but they are doing things that 5 or 10 years ago we could only dream about. The world's best quantum computers can't yet break encryption or solve huge problems, but they can, for example, simulate small molecular structures or run proof-of-concept algorithms that hint at what's coming. Each year, new milestones are announced, a new record in qubit fidelity, how accurately a qubit operates, a demonstration of a quantum error-correcting code working on a small scale, or a new quantum algorithm that might one day be useful for chemistry or optimization. It's a field moving forward in careful, delicate steps. Now that we have this context, let's take a closer look at what all these ideas really mean. We encountered words like quantum bits or qubits, superposition and entanglement along our historical journey, at least in passing. Now, in a slow and simple way, we will explain these concepts and how a quantum computer actually works when it uses them. It's okay if some of it still sounds mysterious. We'll keep everything very gentle and clear. So let's delve deeper into the heart of quantum computing, step by step, under the soft light of understanding. Now, what exactly makes a quantum computer different from the classical computer on your desk or in your pocket? The secret lies in those quantum bits we mentioned, usually called qubits. We already touched on the idea that a qubit can do something a normal bit cannot. It can exist in a superposition, meaning it can be both 0 and 1 at the same time, in a sense, until we look at it. This is a mind-bending idea, so let's go through it slowly and gently. Imagine a classical bit as something simple like a coin that you can lay on a table. Heads could represent 1 and tails represent 0. In a classical computer, every bit is like a coin lying flat. It's clearly showing either heads 1 or tails 0. Now imagine I take the coin and give it a slow spin on the table. While it's spinning, you can't really say it's heads or tails. In that moment, it's sort of both, blurred in possibility. Only when it eventually comes to rest and you stop it with your hand do you see a definite heads or tails. That spinning coin is a bit like a qubit in superposition. As long as we leave it alone, not measuring it, it maintains a combination of both 0 and 1 possibilities. It's not that the qubit is literally 0 and 1 in a clear-cut way, but mathematically it's in a state that encodes both. And when we finally measure the qubit, analogous to catching the coin, it randomly gives us either a 0 or a 1, with probabilities that depended on how it was spinning, the details of its state. Superposition is a peaceful but powerful idea. it means one qubit can explore multiple pathways at once. But just having a qubit in superposition isn't enough to guarantee a useful computation. After all, if you just spin a coin and get a random result, that's not obviously helpful. The real magic comes when we have multiple qubits and another quantum phenomenon called entanglement enters the picture. Entanglement is something even Einstein struggled to accept, calling it spooky as we mentioned earlier, but experiments have shown it's very real. So what is it? Let's imagine we have two qubits that become entangled. It's as if these two qubits are now connected by an invisible thread. Not a physical thread, but a thread of information. When two or more qubits are entangled, their states are linked together in such a way that the whole system has to be described as one. If we go back to our coin analogy, entanglement is a bit tricky to illustrate, but think of two coins spinning in sync. Maybe they are far apart, one in one room and one in another, but somehow they are spinning in a coordinated way. If you stop one coin and it lands on heads, the other coin, no matter how far away, might instantaneously respond by landing on tails, as if they were choreographed together from the start. In reality, with qubits, it's not that one physically causes the other to flip at the last moment, but rather that their joint state was set up so that they are opposite or the same when measured. It's as though the two entangled qubits share a single existence across space. Only when you measure them do you see the specific outcomes, but those outcomes will be correlated in a way that defies classical intuition. Entanglement allows quantum computers to do something extraordinary. It lets information be spread out across multiple qubits. In a sense, two entangled qubits act together as a unit. If you have many qubits entangled, the quantum computer can process an immense number of states simultaneously, because every additional entangled qubit doubles the amount of information the system can hold in superposition. With entanglement, qubits aren't just individual little coins spinning on their own, they become part of a larger, intricate dance, where each qubit's state is deeply connected to the others. This is crucial for quantum computing's power. Now, there is another piece to the puzzle of how quantum computers work: interference. This is a phenomenon that arises because quantum states behave like waves, much like ripples on the surface of a pond. Think of what happens when you drop two pebbles into a still pond. Each pebble creates expanding waves that move outwards. Where the waves meet, they interfere with each other. Sometimes the water peaks higher, where two wave crests meet and reinforce, and sometimes it becomes very calm, where a crest and a trough meet and cancel each other out. Quantum particles, and hence qubits, have a kind of wave nature too. When a qubit is in a superposition, you can imagine it as a kind of probability wave for being 0 or 1. When you have many qubits and entangle them and let them evolve, you have waves propagating through all those possibilities. Quantum algorithms are designed to make the waves corresponding to the wrong answers cancel each other out, destructive interference, and the waves for the right answers add up, constructive interference. In the end, when you measure the qubits, when the waves collapse, so to speak, you're left with a high probability of seeing the answer you seek and low probability for outcomes that you don't want. This interference idea is abstract, but we can make it a bit more tangible with another visualization. Picture a quiet room with two speakers playing the exact same pure tone. If you stand in certain spots, the sound might become very loud, where the sound waves from both speakers arrive in sync and reinforce each other. In other spots, it might become nearly silent, where one speaker's sound wave has a crest and the other has a trough, cancelling out. Now imagine that instead of sound waves, these are waves of probability amplitude inside a quantum computer's calculation. The quantum algorithm adjusts the volume and phase of these waves such that for the outcomes that represent a correct solution, the waves line up and amplify, and for the outcomes that represent wrong answers, the waves misalign and cancel out. It's a delicate and beautiful process, like carefully arranging many waves so that one specific pattern emerges clearly at the end. When you measure the qubits at the conclusion of the algorithm, it's like capturing the final interference pattern. If the algorithm has worked, you'll see the result you wanted with high likelihood. Let's tie this back to those algorithms we mentioned earlier, like Shor's and Grover's, to make it more concrete. Shor's algorithm uses a quantum process to find patterns in numbers. Essentially, it leverages interference through something called the quantum Fourier transform. What you need to know is that all those possible factors of a big number are explored in superposition, and the quantum logic cleverly sets up the problem so that the wrong factors interfere and cancel out, and the right factors stand out. So when the final measurement is made, the correct factor, like the secret factors of a large semi-prime number, pops out with high probability. Grover's algorithm, in a simpler sense, starts with a superposition of all possible answers, say all entries in an unsorted list, and then it applies an operation that inverts the amplitude, the wave height of the correct answer relative to the others, and another operation that interferes all these possibilities with each other. After a few repetitions of this process, the correct answer's amplitude gets boosted higher and higher while all other possibilities get suppressed. In the end, measuring the qubits yields the answer you were looking for, more often than not. It's okay if this still feels a bit mysterious. In truth, it is mysterious, even to physicists. But the key takeaway is, a quantum computer isn't just a faster version of your laptop. It works in a fundamentally different way. It sets up a kind of massive multi-wave calculation where all outcomes are explored at once in a tangle of superposition and entanglement, and then it uses interference to sift through those outcomes and extract the answer. Unlike a normal computer, which carefully checks possibilities one by one in sequence, a quantum computer sort of spreads out the problem and lets the answer emerge from the interplay of probabilities. It's a bit like finding the way out of a maze by figuratively exploring all paths at the same time and having the wrong paths cancel themselves out. Now you might wonder, how do we actually do any of this in practice? What does a real quantum computer look like or feel like? It's a great question because quantum computing sounds very ethereal and abstract. In laboratories and companies around the world, quantum computers are being built in various forms, and they do have a physical presence, often an impressive one. If you were to walk into a lab where a superconducting quantum computer is housed, you might first notice a large cylindrical structure that looks a bit like a fancy chandelier or a steampunk art piece. It's often a tall stack of shiny metal plates, rods and wires, usually encased in a protective shell. This contraption is actually a dilution refrigerator, essentially a very powerful freezer, which cools the quantum processor down to extremely low temperatures, colder than outer space, often around 0.01 degrees above absolute zero. At the very bottom of this fridge, in a space smaller than a coin, sits the quantum chip. Tiny as it is, on that chip reside the qubits. For a superconducting system, the qubits are tiny circuits made of superconducting materials. Dozens of gold wires connect to the chip, carrying microwave signals that control the qubits or read out their states. When the machine is running, you might not hear very much, perhaps the hum of the cooling system, but essentially it's quiet because these computations don't involve whirring parts, just electromagnetic pulses sent into the cold chamber. It's a very calm scene in a way, a quiet, cold refrigerator in a lab, diligently keeping the qubits isolated from the noisy world outside. This isolation is necessary because any stray heat or electromagnetic noise could disturb the qubits and cause them to lose their quantum state, that is, to decohere. In another type of quantum computing lab, say one focused on trapped ions, the setup looks different but has its own kind of quiet beauty. You might see a table full of lasers and mirrors, gently humming and glowing. At the center, there's a vacuum chamber, a metal container from which all air has been pumped out. Inside that chamber, with the help of electric fields, a string of ions, charged atoms, is levitating, held in place as if by an invisible hand. Each ion in that string can act as a qubit. Its internal energy states serve as the 0 and 1, or its spin, or some other quantum property. The lasers are pointed into the chamber and they strike the ions with such precision that they can flip the state of one ion or cause two ions to become entangled by mediating interactions between them. If you were to look at directly, not recommended without special goggles, of course. You might even see a faint glow from the ions when they are fluorescing. It's almost poetic. Tiny points of light suspended in darkness, each one a qubit holding a quantum state, being written to and read from by gentle laser pulses. Whether it's superconducting circuits, trapped ions, or photons traveling through optical fibers, the theme is the same. Qubits are very delicate and need careful handling. They require special environments, ultra-cold or ultra-isolated vacuum, etc., to protect their quantum nature. When a qubit loses its quantum state, we say it has decohered. Decoherence is like that spinning coin suddenly being jostled so it falls down and shows a random face, or like a delicate soap bubble popping when touched. It's the process of the qubit becoming a regular bit prematurely, before we wanted it to. Every effort in quantum computing hardware is about delaying decoherence long enough to get computations done, and about controlling qubits with exquisite precision without tipping them over the edge. This is where the earlier point about error correction comes in. Even with the best isolation, qubits will sometimes flip or errors will creep in. Quantum error correction is a set of techniques that, interestingly, use more qubits to protect the information in one qubit. It might sound counterintuitive, using more fragile things to protect a fragile thing, but by entangling multiple physical qubits in just the right way, they can encode one logical qubit of information such that if one of them goes astray a bit, the error can be detected and even corrected by a corresponding operation without directly measuring and disturbing the quantum information. In essence, the extra qubits act like guardians, watching for any sign that the main qubit's state is drifting and then helping to set it right. This is very complex to implement. It requires a lot of physical qubits and very high control fidelity, which is why we haven't yet seen a fully error-corrected large-scale quantum computer. But small demonstrations of error correction are happening. It's a bit like having 3 or 5 spinning coins all linked together to represent one logical coin flip. If one coin starts to wobble wrong, the others have a way to compensate and get it back on track, all without ever having to stop the coins from spinning. When you put all this together, you get a picture of how a quantum computer works, at least at a conceptual level. To summarize in plain terms, we prepare some qubits in a controlled starting state. Often all qubits start as 0, analogous to all coins showing tails. We then apply a carefully choreographed sequence of operations, quantum gates, to these qubits. During this sequence, the qubits get put into superpositions. They become entangled with one another, and their probability waves flow and interfere through the computation. The sequence of operations is the quantum algorithm, crafted to make the right answer build up constructively. Finally, at the end, we measure the qubits. This collapses their states to definite zeros and ones, like catching all the spinning coins, or opening the boxes with Schrödinger's hypothetical cats, if you know that famous thought experiment. We don't actually see the quantum waves or the entangled spirit of the computation directly. We just see the final bit string of output, ordinary zeros and ones, that we can read like the answer to a problem. But if the quantum algorithm and hardware have done their job, those ordinary bits we read out carry the solution to whatever problem we encoded, found by means that no ordinary computer could imitate. It's quite magical in a way. The computer, during its brief moments of calculation, was living in a kind of richer space of possibilities, exploring so many paths at once, and then by the end, collapsing that richness into one actual answer that we care about. All of this happens typically in a fraction of a second for current quantum computers. Their coherence times are often microseconds to milliseconds, and algorithms usually need to finish within that time frame before decoherence sets in. Yet, in that ephemeral moment, a whole quantum dance takes place. It's worth noting that despite the wonderful potential, quantum computers today are still limited in what they can practically do. If you run an algorithm on a real device, you might have to deal with a lot of noise and errors in the output, requiring the calculation to be repeated many times to get a clear result. Researchers spend a lot of time figuring out how to tweak algorithms to be shorter, or how to filter out noise from results, kind of like like trying to hear a faint melody in a room with some static. This is the reality of being in the NSQ era we mentioned. It's like learning to walk before we can run. And it's why so much research is focused on improving qubit quality and error rates. Even with these challenges, one can't help but marvel at what has been achieved so far. We have seen quantum computers perform small versions of tasks that would take impractically long on any supercomputer. We have seen entanglement stretched across dozens of qubits. We have seen, essentially, human ingenuity beginning to direct the oddness of quantum mechanics towards computation. Remember, all of this was just a theoretical idea decades ago, and to witness it become real is a testament to how far science has come. By now, we've covered a lot: the history, the principles of how quantum computing works, and glimpses of what these machines look like and how they operate. It's a lot to absorb, but you don't need to remember every detail. The beauty of learning in this gentle, half-asleep way is that some ideas will settle in your mind naturally. You might just carry an intuition that quantum computing leverages something very different: superposition, entanglement, interference to process information. Even if the specifics are hazy, and that's perfectly fine, the general impression is what matters. That there is a new kind of computing emerging, one that whispers with the voice of quantum physics. Before we drift away completely, let's take a few minutes to consider where all this might lead in the future. What could quantum computers do for us if we continue to improve them? When we gaze toward the future of quantum computing, we do so with quiet hope and cautious optimism. As the technology matures, the implications could be profound across many fields. One of the areas people often talk about is cryptography and security. Recall how we mentioned that Shor's algorithm could break certain encryption schemes by factoring large numbers. This means that once sufficiently powerful quantum computers exist, some of the codes that currently protect our online information, like financial transactions, private communications, and state secrets, could be broken. In practice, it would likely require thousands or even millions of quantum bits working together with error correction to actually break the strongest codes we use today. So that scenario is not immediate. It gives the world time to prepare and adapt. That sounds alarming, but the world is not sitting idly by. Even now, researchers are developing new forms of encryption, often called post-quantum or quantum-resistant cryptography, that quantum computers won't easily crack. And quantum computing itself offers a solution in the form of quantum cryptography, using quantum mechanics to secure information in ways that are theoretically unbreakable, thanks to the laws of physics. For example, quantum key distribution allows two parties to share secret keys with the guarantee that if anyone eavesdrops, the quantum states will be disturbed and the intrusion noticed. So in the future, quantum computers and quantum communications might work hand in hand. Quantum computers on one side posing new threats to old encryption, but quantum techniques providing new, stronger safeguards. It's like an evolving landscape of security, and it's pushing us to innovate continually. Another huge potential area is medicine and drug discovery. Molecules behave quantum mechanically at the smallest scales, and simulating them accurately is extremely hard for classical computers. A quantum computer could natively simulate quantum systems, like molecules and materials. This means in the future we might use quantum computers to design new medications by modeling complex biochemical interactions atom by atom, or to create new materials with desired properties by understanding chemical bonding in detail. For instance, finding a catalyst that efficiently pulls carbon dioxide from the atmosphere, or discovering a new protein structure for curing a disease. These problems involve enormous numbers of possibilities and quantum-level interactions. A powerful quantum computer could potentially explore those possibilities much faster than a classical computer, acting as a kind of virtual laboratory. Imagine being able to test millions of molecular variations in silico overnight, rather than synthesizing each one in a wet lab. That could accelerate the pace of discovery in healthcare and materials science dramatically. Then there's the field of optimization and artificial intelligence. Our world is full of complex optimization problems, routing airplanes efficiently, optimizing supply chains, traffic flow, financial portfolios, or even the way machine learning algorithms train on data. Some of these problems are so complicated that even our best classical algorithms struggle with them as they scale up. Quantum computers have special algorithms, some known, some yet to be discovered, that might provide speed-ups for optimization. A method called quantum annealing, which D-Wave's machines explore, is one approach tailored to these kinds of problems. Though the current quantum annealers have not definitively beaten classical methods for most real-world tasks, future, more advanced quantum processors might tackle certain optimization tasks with ease. Imagine being able to find the absolutely optimal way to schedule thousands of delivery trucks, or to route electricity in a grid so as to minimize loss, or to allow an AI to consider many more potential solutions to improve its learning. These are the kinds of improvements we hope quantum computing might deliver. Speaking of artificial intelligence, AI, the synergy of quantum computing and AI is an exciting possibility. There are already ideas and early research on quantum machine learning, algorithms that use quantum computation to analyze patterns in data or to train models. One day, a quantum computer might be able to handle datasets of enormous size or complexity, or find subtle patterns that classical computers would miss by leveraging its ability to do many computations in parallel via superposition. This could potentially lead to advances in how we predict weather and climate patterns, how we model economic systems, or how we design intelligent systems that can make decisions or recognize complex patterns like medical diagnoses from scans or intricate trends in finance. It's early days for quantum AI, but many experts think that as quantum hardware grows, it could become a powerful tool in the AI toolbox. It's a bit like adding a new intuition or a new sense to the computational mind, a different way of processing information that could complement classical methods. Another domain to consider is scientific research and fundamental science. Quantum computers could help us probe the mysteries of physics itself. For example, they might simulate high-energy physics processes or quantum gravity scenarios that are beyond the reach of current experiments. They might also help in understanding quantum chemistry of exotic materials that could lead to high-temperature superconductors or new energy sources. If we think even further, some imagine using quantum computers to search through data from particle colliders or telescopes for faint signals or patterns, maybe even to help analyze signals that could indicate new physics or extraterrestrial communications. These are more speculative, but they highlight that the impact of quantum computing could extend to answering fundamental questions about the universe. In more everyday terms, for the average person, the rise of quantum computing might not be directly visible at first. You might not have a quantum laptop, and likely never will, in the sense of a device you carry around, because quantum computers will probably remain specialized machines, much like supercomputers are today, possibly accessed over the cloud. But indirectly, the services you use could become better thanks to quantum computing on the back end. Perhaps your medication is discovered faster, your smartphone batteries last longer because a new material was designed with quantum help, or your online transactions are secured by quantum cryptography. Perhaps traffic in your city flows more smoothly because a quantum-optimized system times the lights or routes vehicles more efficiently. These changes, if they come, will likely roll out gradually and behind the scenes. One day, you might read a news headline that says a quantum computer solved a problem that was unsolvable before, and then a year or two later, you might notice the effects in your day-to-day life without ever directly touching a quantum machine. It's also possible that quantum computers will enable new technologies we haven't even dreamed of, much like classical computers did. When the first electronic computers were built in the mid-20th century, no one at that time envisioned things like the internet, smartphones, or machine learning as we have today. In a similar way, the unique abilities of quantum computing might open doors to innovations that are hard to predict right now. We can imagine, though, that any field where complexity is a barrier whether it's designing a new airplane with quantum fluid dynamics, forecasting complex economic outcomes, or even generating new kinds of art and music through quantum-inspired creativity, could be touched by this technology. The future horizon is wide, and quantum computing is one of the tools that may help us explore it. Now, it's important to approach these possibilities with a calm perspective. There is a lot of hype around quantum computing, and while it's justified that the potential is huge, the timeline of reaching that potential is uncertain. Many experts believe that achieving fully error-corrected, large-scale quantum computers might take on the order of a decade or two, or even longer. We are still in the stage of refining the basic components. So while we dream of these applications, we also understand that patience is key. The progress will be steady, and occasionally there will be leaps, but science has its own pace. In the meantime, classical computers will also be improving, and they won't be standing still either. Plus, we often find hybrid approaches, quantum computers working in tandem with classical ones to get the best of both worlds. So the likely scenario is that quantum computing will gradually augment classical computing rather than suddenly replace it. We'll see a period where certain tasks get offloaded to quantum processors, perhaps through cloud services, while everyday computing stays classical, and together they achieve things neither could alone. All this is to say, the future of quantum computing is bright and intriguing, but also unfolding gently over time. Each year brings new progress, and as engineers and scientists solve one problem after another, those far-off applications come closer into reach. We can imagine a future where a scientist with a tough research problem doesn't say this might take years to compute, but instead can ask a quantum computer to handle the heavy lifting. Or a future where sensitive communications are routed through quantum channels that we trust, in a deep sense, to be private. We can imagine life-saving drugs discovered more swiftly by quantum simulations, or complex logistical challenges like deploying aid in a disaster being solved in moments by a quantum optimization algorithm. These are the kinds of things that make people passionate about developing quantum technology. As we envision these possibilities, let's take a moment to appreciate how far we have come and how these future dreams rest on the delicate experiments and theories of today. The quantum physicists of the early 20th century opened the door to this strange quantum reality. The computer scientists and engineers of the late 20th and early 21st centuries began to build the keys to harness it, and in the coming years, many brilliant minds will continue working to turn those keys and unlock capabilities that, for now, lie behind the door. It's a journey, much like the one we took tonight through history and concepts, step by step, discovery by discovery. And we are lucky to witness the dawn of this new era. Just as classical computing transformed the world in ways people barely imagined, quantum computing may quietly do the same in the years ahead, weaving into our lives gradually and subtly, improving things in the background. The night is deepening, and we've gently traveled through a vast expanse of knowledge. From the tiny quantum sparks of the early 1900s, through decades of curiosity and discovery, to the quiet hum of quantum machines in modern labs, it has been quite a journey. Think back for a moment to those early insights. How energy comes in little quanta, how particles can behave in strange ways. Remember how we talked about a coin spinning in the air, a simple image for a qubit's superposition, and the idea of two coins spinning together, mysteriously linked. That was our gentle metaphor for entanglement. These images and ideas might float softly in your mind. You don't need to grasp them tightly, just let them drift like leaves on a calm pond. We explored how a quantum computer weaves these principles together. Superposition, entanglement, interference. These were the three gentle muses of our story. Perhaps you can almost see them as characters in this nighttime tale. Superposition. The ability to be many things at once, like a whisper of possibilities. Entanglement, the bond that ties distant objects together in unity, a silent connection. And interference, the pattern of waves that brings clarity from chaos, quietly selecting the truth from noise. They work together in harmony inside the quantum computer, guided by careful hands and clever minds. All of this happens in spaces we barely see, inside tiny chips at the bottom of ultra-cold refrigerators, or among trapped ions glowing in a vacuum. It's almost magical, yet it's grounded in real physical experiments carried out by dedicated scientists and engineers. As we look back on what we've learned tonight, let's do so gently, without any rush. We saw how visionary thinkers like Feynman lit the way with ideas, and how pioneers like Shaw and Grover provided maps in the form of algorithms for this new territory. We saw how, bit by bit, qubit by qubit, the dream of quantum computing moved from imagination to the laboratory bench. And we gazed ahead at what might come, the medicines that might be discovered, the problems that might be solved, the mysteries that might be unraveled, all with the help of these remarkable machines that leverage nature's own quirks. It's a lot to take in, but there's no need to hold on to all of it now. In the same way that a gentle sleep allows our minds to sort through the day's experiences, you can let your mind sort through these ideas in its own time. You might find that even in sleep, some of these concepts settle in, or perhaps they simply provide a soothing backdrop for pleasant dreams. Feel the weight of your body sinking into the bed and notice your breathing, soft and slow. With each breath, you can imagine exhaling any remaining alertness or effort. There is no quiz at the end of this, no task to perform, just the quiet understanding that you have spent this time enriching your mind, even as you unwind. Quantum computing, in all its complexity and promise, has been our companion this evening, but now it too will gently recede into the background of your thoughts. If your mind drifts to the image of a spinning coin, let that image spin away into darkness when it's ready. If you recall the image of ripples on a pond interfering with each other, you can imagine those ripples gradually smoothing out into a glassy, calm surface as night settles. Any entangled coins or particles in your thoughts can dissolve, untying into simple, peaceful rest. All the technical details and facts we talked about can now float off like dandelion seeds in the breeze, carrying the knowledge to a safe, quiet corner of your mind where it will be kept. You don't need to do anything more. The world of quantum computing will continue its quiet march forward, but for now, you can simply be still and content, knowing you've peeked into something profound and interesting. In this moment, nothing matters except your comfort and rest. Feel free to let go of the day's concerns, and also let go of these words as they fade out. Your eyelids may be heavy, your body relaxed. Let the softness of sleep come to you. Thank you for joining this gentle journey with me. May your dreams be pleasant and your rest deep. We have unraveled a bit of the quantum mystery tonight in the most gentle way, and now it's time to relinquish even that and surrender to the quiet night. Good night.